Okay. Can you hear me now?
Yes, ma'am.
Okay, okay. Thank you. All right. So let's start with week two. Are you able to see my screen as well?
Yes, ma'am.
Okay.
Yes, ma'am.
Thank you. Thank you.
Ma'am, is it recording?
It is live streamed and it is also being recorded.
Okay, super.
All right. Uh, okay. So so far, like in week one, what we have seen is like if you have the data set, how can you find your principal components um, and how many times you have to repeat the process, right? So we have seen all this, but there were two issues that has been discussed here, right? So the very first issue was like if you have non-linear relationship between features. So if you have non-linear relationship between features, then what do we do in that case? So how do we figure out like which important, which features are important and which are not? Like for example, if your data set lies in a circle, right? Then in that case, the variance along both the directions, and if, let's say these are my principal components, then it's very difficult to figure out like what which directions are important, right? So how do we deal with such kind of problem, like when there's like non-linear relationship between features are? So, for example, let's say I have features. Let's say I have a data point X, which has two features, F1 and F2. Okay, and if I'm talking about a data set which lie on a circle, so this is my circle, and let's say this is my center of the circle. So let's say the center, if we give it as by A and B, then how can we write this relationship uh, between these two features? We can see that this is nothing but uh, an equation of a circle. I mean, these points are lying on a circle. So what we need to write or what we need to figure out is that what is that equation of a circle, right? So we can see that the center given to us is a comma b, right? So how do you write the equation of circle? It is going to be x1 minus the first component of this. So in this case, f1 minus a whole square plus we will have f2 minus b whole square, right? And this should be equal to, let's say, it should be sum r square. This was center, right? So let's say this is x naught. This is how you will write the equation of circle.
Ma'am, your
Now,
voice
if
is
you,
break.
Yeah, ma'am,
oh,
it's a bit fluctuating.
it's, is it better now?
Ma'am, not breaking, it is not clear actually.
It is not clear. Okay, I will try to speak a little louder. Is it better now?
Yeah, ma'am.
Okay. So, if we have these two features F1 and F2, and the center is my A comma B, then this is the equation of the circle that we will have, right? Now, let's open it. So, what do we get? We get F1 square plus F2 square plus A square plus B square minus 2A F1 minus 2B F2 minus R square is equal to 0, right? So what do we currently have is we have a point x which is given by f1 and f2, and what we want to do is for this feature I want to map this to some higher dimension, and that mapping is given by phi, right? So I want to move this f1 f2 to some higher dimension, and what can be what mapping can be defined here? So let's say all the constant that we have, which is a square plus b square minus r square, this is the constant, right? So for that, for these constant, I can just give the weight as 1. Now we have f1 square, f2 square minus 2a f1 minus 2b f2, right? So I will have f1 square, I will have f2 square. I think it's something f1 square, f2 square. Then I have f1, then I have f2, and then let's say there is this f1, f2 product. Okay. So what are we doing is that we are saying there is some data point which is initially in R2. Okay. So currently, let's say this point is in R2, this X is in R2.
Ma'am,
Now
can
we
you
are
repeat
moving
what you
this.
just said because your voice is not very clear to me.
Yeah, ma'am, can you check your
Okay,
microphone?
let me see. Wait. Is it better now? Can you hear me?
Yes.
Namaste.
No, ma'am. Video quality is down.
It's not visible.
It is
It is visible.
Okay. Is the voice better?
It's okay.
Uh, all right. Let's see. Okay. So this part, right? We were doing this part. So what I said is we have currently the data point in R2, and now we are mapping this to a higher dimension, right? So when we wrote the equation of the circle, this is this correct. Now this can be written as this. Till here it's okay. No doubt till here.
Yes, ma'am.
Okay. Now what we are saying is that this part we can write it as 1 f1 square f2 square f1 f2 f1 f2.
Ma'am,
And
how
then
to
we'll
get this?
again no, again we'll have to so these constant that we see, so my a square plus b square minus r square, these are constant. So my a square plus b square minus r square is a constant term. Now what we have is this f1 square, this f2 square, then I have this f1, then I have this f2, and I don't have any term in f1 f2. So I'm not I mean we are not doing anything about this right now. So we need to see like how
Ma'am, your
to
voice is
write this
breaking.
mapping. Is it for everyone?
Yes, ma'am.
yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Ma'am, no, if it possible, can you use headset? No.
If it's possible, what?
Like, can you use headset?
Okay.
Uh, um, so that the microphone.
Is this better?
No, ma'am, no.
Now the voice is better.
No, ma'am.
No.
Ma'am, I think your mic is not working properly.
Can you connect through mobile phone, ma'am?
In sharing, there is no problem, right? Only the voice is a problem for you.
Yes, ma'am.
Uh,
Ma'am, video
Ma'am,
quality is
use
also
another
low.
device to mic.
what about now? Is it better? Okay.
Yes, ma'am.
Okay. Yeah. Okay. All right. So, we were here. Okay. We were doing this. Now, what we are saying is like if we take any let's say any a any vector we take in, let's say v is a vector in R6. Okay. So if that's the case, then I can write v to be. What are the coefficients that we took? So one was a square plus b square minus r square. So a square plus b square minus r square. For f1 square, it is going to be just 1, right? For f2 square, you only have the coefficient to be 1. So again 1. Then f1, f2. For f1, we have minus 2a. For f2, we have minus 2b, right? So f2, we have minus 2b. And then we have f1, f2, we have 0 basically, right? So if we can multiply these two, so if we can multiply, if we take this vector, which is in R6, and if we take these, I can get this equation. Is this okay? Like we can get this equation if we multiply these two.
How F1, F2 is 0?
How f1, f2 is 0? Because if you look at this equation, right? This equation of circle that we have done, this equation.
Yes,
Now
ma'am.
there is no f1, f2 term, right? So if there is no f1, f2 term, and I know there can be some relationship between f1, f2 as well. So we have put this here in the vector, which is
Yes,
f1,
ma'am.
f2. But now if we have to write this equation of the circle, then what will you do? This, you will take this vector, which is currently 1, f1 square, f2 square, f1, f2, and f1 times f2, right? And you will multiply this with this vector, correct? So you have a square plus b square minus r square. You have 1, 1, minus 2a minus 2b, 0, right? This will give
Ma'am,
you the equation of the circle.
ma'am, can you tell me the first term? How did it come?
A square plus b square minus r square.
Yes.
So this is coming from here. Like equation of the circle, we have this a square plus b square minus r square term, which is a constant. Like you see, they don't have any dependency on f1, f2 or f1, f2, right? So this
Yes.
is nothing but a constant. So that's why we have taken the coefficient to be 1 here. And that's how this 1 is getting multiplied with a square plus b square minus r square.
Okay.
Okay?
Ma'am,
So, yeah,
is this for this specific case or like can be generalized to any non-linear?
this is for the specific case. This is for the specific case.
Okay.
Okay.
Ma'am, can you remove
So
this screen where we can see the students from the whiteboard?
uh,
Remove the pop-up screen.
okay, can I remove the screen? You're seeing the screen as well.
Yes.
Okay.
Ma'am, I mean, the pop-up when you share the whiteboard.
Okay. This part, right? What if it closes? Is this? Are you able to see
Yes,
now?
ma'am. Now okay.
Yes.
Yes,
Yes,
yes.
ma'am.
Okay, fine. So this is what we have. Okay. Now, in general, if we want to see this, so let's say I have some two vectors. Okay. I have this x1 and I have this x2. Let's call this x to be f1, f2, and let's call this x2 to be g1, g2. Okay. So if these are your vectors, and suppose we define a function which is let's say f of, let's call this x. So combine
Ma'am, your
x1,
voice breaking away. Yes, sir.
oh, okay. Is it better now?
Yes.
Okay. So what I'm saying is, let's say define a function, okay? And what is that function? That function is that I take x1, I take x2, plus you add something to it, some constant, okay? Now, if you take the square, if you take the square of this, then what happens? What is x1? X1 is f1, f2, but we are taking its transpose. So we have f1, f2, right? What is x2? This is g1, g2, right? Plus you're adding 1 to this. Okay. Now what happens? If you multiply this, you get f1, g1 plus f2, g2 plus 1 square, right? This is okay?
Yes,
Yes,
ma'am.
ma'am.
Okay. Now this is nothing but you have to take the square of this. So what will you get? You will get f1 square g1 square plus f2 square g2 square plus 1 plus 2 times f1 g1 f2 g2 plus 2 times this, right? So 2 times f2 g2 plus 2 times f1 g2. This is okay.
Yes.
Uh, Now what happens? So again, we'll have to take f1, f2, f1 and f, like we'll have to separate basically f and g. Okay. So if we have to separate this f and g, then how can we write this? Okay, can someone tell me? Like it's the same as what we did previously. In the previous example, we wrote that equation of circle in form of two vectors. Now similarly, how can we write this term that we have currently?
F1, F2.
Yeah, tell me. F1,
F1 square,
f1 square, f2
F2
square,
square, 2
under
F1.
root 2, under root 2, under root 2 f1 f2,
Yes,
under root 2 f2,
F,
under root 2 f1,
F1.
right? Now
Yes,
for the g, we will write g1 square,
G1 square.
g2 square, under
Under
root
root
2 g1
G1.
g2, under root 2 g2, under root 2 g1. But again, there was this one term, right? So I need to add this one over here. So let's add one here. So there will be one on top. This is fine.
ma'am.
So, yeah.
Instead of root 2, can we take 2 in first
No, you
and
can't. You can't. Why? Because now this I am calling it as, so what
what we had was this vector in 2 dimension, right? We had this f1, f2, right? Now we
Yes,
are mapping this, which is in R2, to a which dimension? 1, 2, 3, 4, 5, 6. We are mapping this in R6 using this phi function. Okay. So we are, what is phi doing? Phi is taking your x, right? Which is your f1, f2, and it is converting in R6, which is this vector. In general, if you have to write for this, what will you write? You will write 1 f1 square, f2 square, under root 2 f1, f2, under root 2 f2, and under root 2 f1. Okay. So, and this is also your phi basically, right? It just for different x now you take different x now, instead of f1, f2, I took g1, g2. Then that is giving me this function, this vector, right? But the function, underlying function is the same. This phi, the mapping that is taking your vector array from R2 to R6, that is same, right? So what we are able to do now is we are able to write this x1 transpose x2 plus 1 square is equal to phi of some phi times, or phi transpose phi, right? Or to say phi of x1 transpose phi of x2. This
okay,
is okay?
ma'am. But okay, but still also I don't understand why we are taking root instead of two.
Why we are?
Maybe because of it's a mapping now, so it should be generalized to whatever we throw in it.
Yeah, we have to generalize it, right? Because see, if you write let's say 2 here, then what happens in the other side? You just have g1, g2, but this is on this side you have 2 of f1, f2. So the mapping that you're defining is not going to, it's not it's not correct here, right?
Okay, ma'am.
Because you're saying this phi is taking your R2 to this vector, but on the other side, you're saying your phi is taking this x from R2 to this vector. So your mapping should be same, right?
Yes, ma'am.
Okay. So this was about yeah. So what we did is we wrote this x1 transpose x2 plus 1 whole square to be phi of x1 transpose phi of x2. Okay. So we'll see why this is useful later. So this will come. We'll come to this. This is just to introduce. We have discussed this. Okay. But we will see why this is useful. What we have done here, why this is useful, we'll see. We'll mark this as star. Okay. So let's go back to the PCA part. Okay. Just one moment. Okay. So we'll go back to the PCA part. Now, what were we doing in the PCA? The very first thing was we had our data set in D cross n dimension. What were we doing next? We had to, like, once we have the data set, we wanted to find the principal component. Find principal component. Okay. So we wanted to find the principal components. Now, to find the principal components, what did we do? We found the covariance matrix, right? And this covariance matrix C was in D cross D dimension this time, because this was what is like this covariance matrix was 1 upon n x axis transpose. So which is basically D cross D dimension. Now, once we have the covariance matrix, what we will do? We find the eigenvector. We find eigenvector and we find the eigenvalues. Right? Basically, we do the eigen decomposition of this matrix C. But now, like the issue that we had was, let's say we have this D to be very large. Like in case your number of features, if D is very, very large than n, then solving this matrix, like once you have this covariance matrix, finding its eigen decomposition, that is finding the eigenvector, eigenvalues, it's going to be very competitive. Like it's going to be very tough to. It will take a lot of time, basically, right? So how do we deal with this such bigger dimension? Like how do we find its eigenvector? How do we find its eigenvalues? So this is the problem that we have to solve here. Question.
Ma'am,
Yeah.
so in the lecture, no, sir has taken it as X transpose X. So, like, are you taking X as n cross T matrix?
Um, no, sir has taken this only, right? Covariance matrix is XX transpose.
Yeah, we will use
Yes, I think
X
it was in-
transpose X when D is smaller than N.
This is okay, right?
Yes, covariance
Um,
matrix is X.
so you have X in D cross N. The covariance matrix is XX transpose divided by N, right? And then we find the eigenvector and eigenvalue for this covariance matrix C. Okay, this is what we do. But in case your D is quite large, which is your covariance matrix will be in D cross D, but if your D is very large, then how computing this eigenvector and eigenvalues are going to be a very time consuming, right? So how can we find this eigenvector is what we have to see. So the question is, and why are we interested in finding the eigenvector? We are interested in finding the eigenvector because they are giving us the principal components. So how do we get principal components? This is the question. So if you look at this, if C is your matrix for which you want to find the eigen vectors, then what is the eigen equation that you know? It should satisfy C of W to be equal to lambda of W.
Ma'am, your voice breaking again.
Uh, uh, is it breaking again? Okay, you keep yourself on mute. Okay, so C of W, lambda of W, this is fine. Then what is lambda?
No,
Lambda is going
ma'am,
to be the
it's breaking.
eigenvalue corresponding to the uh, eigenvector W is going to be the eigenvector corresponding to your eigenvalue lambda, right? This is okay.
Yes, ma'am.
Now, what is the C? And in general, if we are interested in like kth principal component, then we can write C of wk to be lambda k wk, right? Now if we can write this, then what happens? What is C? My C was nothing but 1 upon n sum over xi transpose, where I is varying from 1 to n. And you have wk as the eigenvector. And this is equal to lambda k wk. Okay. So if that's the case, then I can write my wk to be equal to, I will take this lambda k down. So this is going to be 1 upon n lambda k sum over xi transpose, I varying from 1 to n. Right? N times wk you will have. Is okay? All right. So now what else can we do here? So you have this xi transpose here, right? Now this
sir.
if can
இதுதான்
you
அந்த
mute yourself?
மெடிக்கல் சர்டிஃபிகேட் ஏதோ அப்லோட் பண்ணணுமா?
Can you mute yourself?
ஐயோ என்னத்த சைன் வாங்குறது?
Who is there?
என்ன டெஸ்ட்?
Prakash.
Okay, mute. Okay, I'm muted. All right. So this is
எதுக்கு இது மாதிரிலாம் செட் டெஸ்டிங்?
what happened.
Prakash, your voice is on.
Prakash, mute yourself.
Where is he?
I'm in the peoples. You can search for this name.
Yeah, I'm looking for it. Why is it not showing me?
ஒரு டேர்முக்கும் பண்ணணுமா இது? ஐயோ எதுக்கு தான் இப்படி சாவடிக்கிறாங்களோ தெரியல.
Prakash, can you mute yourself? Where is he? Is it from some roll number or
Name.
Ma'am.
name is there?
You can check
In
the
your-
name. I think.
Okay.
And ma'am, from the people tab, like you can search him by his name.
Yeah, I can
Search
see
him.
him. Did I? Okay, I think it's gone now. Okay. All right. So we were here. We found this WK. Okay. But see that this term, which is xi transpose WK, right? Now this is, I mean, you can keep this together, right? This is associative property. We can have this together. But now this is going to be just some scalar. Okay. So if this is just going to be scalar, I can write this as xi transpose WK xi. So we'll make this change and we will write my WK in this form. So I will write WK to be 1 upon n lambda k, where I is varying from 1 to n. All right. So this is my WK now. And what we can also do is we can just pull this inside. So we will have n lambda k in the denominator. So
Ma'am, what
we
is the
had to
difference
find
between the WK inside and outside?
no, why we did this. So you're asking about this, right? Why we chose to write in this way instead of this way. So what we wanted to see here is that we had this covariance matrix C and we wanted to find this eigenvector W. But if we write, if we write this W to find this W, if we write it this way, we are not able to figure out any kind of relationship between these, right? But if I pull this inside, if I pull this WK inside and write this term as Xi transpose WK divided by N lambda K, then I know that this is nothing but some scalar. This is going to be some scalar, right? Are you all convinced that this is scalar?
Yes, ma'am.
Right? So this is just going to be some scalar quantity. So what we can say from here that my WK, we can write it as some linear combination of data point. So WK, we are saying is some linear combination where Xi is my data point, right? So we are able to write WK as some linear combination of data points. This is the only reason we brought this WK inside inside this. We wrote in this form and not this form.
Yes, ma'am.
Okay. I hope that is clear. Now,
Yes,
if
ma'am.
WK is again, let's start from from the very start. So we had this covariance matrix C. We tried to find the eigenvector for this covariance matrix C. But what we saw that to find this WK, we need the WK itself. This is, even though this is a scalar, but still to find the scalar, to get the scalar, I need the WK. So to find WK, we need WK. So we have to come up with some other alternative for this. So what can be that alternative? So this part, which is WK, which is equal to 1 upon n lambda k, Xi transpose WK, Xi, I varying from 1 to n. We can also write this as, if in the form of matrix, we can write this as X of alpha k. Okay, where alpha k's are this in the matrix notation. So what is my X? What is going to be my X here? Is going to be X1, X2, so on till Xn. And what is going to be my alpha k? Alpha k is going to be my, yeah, coefficient, right? So this is going to be my X1 transpose WK by n lambda k. So on till Xn transpose WK by n lambda k. Okay. So we just wrote in this matrix form where WK is X alpha k. Okay. So we have these two things that we got. So one is the very first thing is that we got is my WK is X times alpha k. And the second was that from where we started is my C times WK, I can write it as lambda k WK. Right. We can do this. This is what we started with and this is what we got. So how can we use this and come up with something? So let's just substitute what my C was, right? So my C is nothing but 1 upon n. So my C was what? 1 upon n. XX transpose, we are sticking to the matrix notation. XX transpose WK, which is X of alpha k. So WK, which is X of alpha k, and times lambda k and X of alpha k. All right. So this, now what we can do is I can pull this n on the other side and what we will have is X transpose x alpha k to be equal to n lambda k x alpha k. Right? Now you just multiply both side of the equation by x transpose. So if you multiply both side by x transpose, so x transpose and x transpose, what do you get? Now I can write this as x transpose x times x transpose x times alpha k to be equal to, now this n alpha k is a scalar. I can pull it out. So n lambda k x transpose x alpha k. Okay. So now we can cancel a few terms here, and what we will get is my x transpose x turns out to be
In lambda k.
n lambda k, right? Yeah, n lambda k. Okay. Or okay, not okay. Let's not remove this alpha k. We'll need that. So see, this x, are you familiar with this x transpose x matrix? We
See,
had started with our
covariance.
covariance matrix x transpose, right? So see this x transpose x. Let's just call it some k for now. Okay, let's just call this k. So x transpose x, I'm taking it as k. Then the equation will have is k square alpha k to be n lambda k k times alpha k. So we'll have k times alpha k to be n lambda k alpha k, where k is my x transpose x. Right? Now, if you look at this equation, can you see if there is some kind of relationship between these terms? Can you see anything?
It's an eigen equation.
It's an
K is n.
eigenequation, right?
Okay.
So this is an eigenequation where you
Can you
have this
please
matrix K,
elaborate
which is
what is
x transpose x.
eigenequation?
So x is equal to lambda x. I mean, if x is the eigenvector of A and lambda is the eigenvalue corresponding to that, you can write eigenequation as Ax is equal to lambda x, right? So in this case, I can say for the matrix K, I can say
Ma'am,
the eigenvector for this is alpha k. Yes.
can you please explain what is eigenequation?
Yeah, this is the eigenequation, no? Ax is equal to lambda x. We started from here. I mean, if you have any matrix A, and you find its eigen, if let's say x is some eigen vector for this, and the eigenvalue is or to say lambda and x are the eigenvalue eigen vector pair, then I can write this. I mean, we can write that in the form of this equation, which is Ax is equal to lambda x. I hope you know this,
Yeah, exactly. Thank you.
right? So same thing we are seeing over here. So what we're saying is that this is K is my matrix. So alpha K, we can think of alpha K as the eigenvector for K. Okay,
And
and
lambda
n
k as
lambda K we can
eigenvalue.
think of eigenvalue for K. Okay. So now once we have this, what can we do? So we got K of alpha K to be n lambda K alpha K. Okay. But what was alpha K for you?
It was a vector with all the
This was xi transpose wk by n
coefficients.
lambda K.
Yes.
Right. So alpha K was xi transpose wk by n lambda K. Right. So what we want is like if and WK was what? WK was the eigenvector corresponding to the covariance matrix. And if you remember, we want our we want our the eigenvectors to have the length 1, right? So the, like keeping that in mind that the norm of WK has to be 1. Now how does what other thing we can what other condition we can put on lambda k alpha k is we have to see. We want the norm of WK to be 1, and the alpha k is nothing but xi transpose WK by n lambda k, right? So there should be some restriction on W, some condition on W, that, some condition on alpha is what we'll have to decide. Okay, so that we will do using. So what was the equation? WK is x alpha k from here. This was the equation. Now if WK is x alpha k, and I know the length of W should be 1, right? So I can take WK transpose WK, right? And if I do that, then I can write this as x alpha k transpose x alpha k. Okay, so this can be written as alpha k transpose x transpose x alpha k. And if the norm of W has to be 1, what we got is that alpha k
Ma'am,
transpose k alpha k should be 1. Yes, tell me.
ma'am, how is this first expression and second expression is equal after
This
taking
one,
the transpose? Yes, yes, ma'am.
this one, and this one.
Yes, ma'am.
How? Okay, they are not equal. They are not equal. We started from here. We started from WK to be x alpha k. How we got this? We showed. I showed you this, right? This
Yes, ma'am.
is there
That is
any
clear.
problem in this? This is clear.
No, no,
So
no,
WK is
ma'am.
x alpha k. This is fine. But what
Yes,
now
ma'am.
we are saying is, since alpha k is equal to xi transpose WK by n lambda k, and we want the WK length to be equal to be 1. Okay. So we want, since WK length has to be 1, then what can we write? What is this length? How do you define this length? It is given by
Uh,
WK transpose WK,
yes, ma'am.
right? So if WK is x alpha k, then I can just substitute WK to be x alpha k over here. So I wrote x alpha k ka transpose times x alpha k.
Okay,
Okay,
got it, ma'am. Got it.
got it. So that's how we got this equation, which is alpha k transpose k alpha k has to be equal to 1.
Ma'am,
Yes.
alpha k is a scalar, isn't it?
Alpha k is not a scalar, no, it's a vector.
Ma'am, how
It's a
alpha
vector.
k value have come?
This is my alpha k. This is alpha. Right. This is alpha k, no? How is it scalar? X is a matrix. Alpha k is a vector. This is your D cross N, and this is your N cross 1.
Okay.
Right?
I thought you are taking
Is
alpha k
okay?
for each xi transpose WK.
No, I couldn't hear you. Can you repeat?
Uh, like I thought alpha k is like each component. Xi transpose WK.
No, no. No, it's a vector. Alpha k is a
Okay.
vector. Okay. So, what did we get so far?
Ma'am, I have a doubt. In alpha
Mhm.
k, how the value have come? Alpha k.
Alpha
Alpha
k we have
equals
not
to
found yet. How did this come? How did this come? Is you're
hmm
asking?
yes, yes.
We showed this. We showed this, right? I mean, we started with C of WK to be lambda k WK. I will just write what all we did so far. So we started with this covariance matrix, and we said, let's say WK, the kth eigenvector is WK, and CWK is lambda K WK. Okay. If that
Okay.
was the, if we solved for this, where we substituted my C to be XX transpose by N, right? And what we got at the end after solving this is that I can write my WK to be X alpha K after solving this. Okay. So after solving this, we got this, where each of the alpha K was given by this X1 transpose WK by N lambda K, so on to Xn transpose WK by N lambda K. And my X is the usual matrix, D cross N matrix, X1, X2, so on till Xn. All right. Then once we have that, we need to figure out some conditions on alpha K that should hold. Okay. So there are two conditions that we came up with. So one was this this condition, which is K of alpha K should be N lambda K alpha K. So K of alpha K, where K is a matrix, K of alpha K to be N of lambda K is the value of the matrix K times alpha K. And the second is that my alpha K transpose K alpha K has to be equal to 1. Okay. So this is what we got. Now, what we will do in the um, this process of doing the PCA, we had to find the eigenvalue and eigenvector for C. It was X transpose, X transpose, right? So instead of doing that, we will take alternate route, and we will, instead of finding the
Ma'am, voice
eigenvalue
is
eigenvector for
breaking.
C, we'll do it now for the matrix K. Um, is it fine now?
Ma'am,
Is
sometimes
it
it's
better? Can you
breaking.
hear me?
Now, now good, but sometimes it's breaking.
Ma'am, can
Okay.
you scroll up a bit? Just
Huh. Here.
like what we
This
do.
side.
Yeah,
Do you want it here or
a bit up.
a bit up? Hmm.
Okay. Okay.
Okay. Now, yeah. So instead of finding the eigenvector eigenvalue for C, we will do this process for K. All right. So what was this K? K was X transpose X, right? And what is C? C is XX transpose divided by N. So let's say we have, we have the eigenvalue and eigenvector for this matrix 1 by N XX transpose to be, let's call the eigenvector to be W1, W2, so on till some WK or WL for all K. Okay. We were denoting the eigenvector of XX transpose by WIs, right? So that's why we'll just stick to that notation. Now let's say the eigenvalues for this was lambda 1, lambda 2, so on till lambda L. But now this relationship is what we are saying. Lambda 1 is greater than lambda 2, so on till this. Okay. So this is what we are
Ma'am, there is
assuming.
lambda L, not lambda
Hmm?
K, in the
Sorry,
last
lambda L,
eigenvalue.
lambda L, yeah. Correct, lambda L. So we have this W1, W2, so on to Wn to be the eigenvector and lambda 1, lambda 2, so on to lambda L to be the eigen values for this covariance matrix C. Right? So if the eigenvalue eigenvector for your covariance matrix C is this, and we know that like the eigenvalues for your matrix X transpose and your matrix X transpose X should be same, right? So
Yes, ma'am.
if lambda i's are the eigenvalues for XX transpose, then what are going to be the eigenvalue for XX transpose? It is going to be n lambda 1, n lambda 2, and so on, right? So this is the eigenvalue for the matrix XX transpose. All right. So now if we take
Why
the
eigenvalue is in times in this case?
because see, your C is what? C is 1 by n XX transpose. And the eigenvalue for C we have taken to be this, right? Now if you do n times C, you're doing what? You want the eigenvalue for XX transpose. So what are you doing? You are multiplying n on both sides, right? So we know that if, let's say, if lambda 1, lambda 2, so on to lambda n are the eigenvalue for the matrix A, then the eigenvalue for the matrix n of A, or let's say 2 of A, is going to be 2 of lambda 1, 2 of lambda 2, so on 2 of lambda n, right? Same thing we have done here. So we multiplied all the eigenvalues by n. Is it okay?
Yes, ma'am.
Okay. So now we have this. So XX, okay. So we got the eigenvalues for my matrix XX transpose. Now what next? So what we're saying is that instead of solving for C, we will solve it for K. So we need the eigenvalue and eigenvector for K, and K is your X transpose X, right? So the eigenvector, say the eigenvector for my X transpose X, the eigenvalues and the eigenvector. So the eigenvalues remain the same, which is n lambda 1, n lambda 2, so on till n lambda L. But the eigenvector, let's say call it as beta 1, beta 2, so on till beta L. Okay. This is for the matrix K, and this is for the matrix C. All right. So we have to take this again. I mean, my beta K has to be in such a way that its length is 1. All right. So now from here, what we want is, see, we started with we had this alpha K with us, but now there is this another vectors that has come in, which is beta 1. Like to solve for Wi's, we got these alphas, right? And now we are saying instead of solving these, to get those alphas, we need, of course, we need to know this WK. So we have to take some alternate route, and that alternate route is through this K, matrix K. Okay. And what we saw is that the eigenvalue for this matrix K are going to be the same, but these are now the eigenvectors. Let's say beta 1, beta 2, so on to beta L. They are the eigenvectors for X transpose X. So now we need to see whether the conditions that my alpha K was satisfying, which was K of alpha K to be equal to n lambda K times alpha K. And the second was that my alpha K transpose K of alpha K has to be equal to 1. So we need to check whether my beta K also does that. And if not, what? Yeah.
Is it norm of K squared?
Norm of K square?
Beta k is a scalar, isn't it?
Beta k is a scalar? No, beta k are the
What is
vectors, no?
beta 1, beta 2?
Beta k are the vectors. They are the
And
eigenvectors
lambda
for
1.
X transpose X.
Oh, these are
N lambda 1
eigenvectors
and
you're
lambda
saying.
2 are the eigenvalues for this K. Okay?
Okay. So betas are the
Okay.
eigenvectors.
Eigenvectors for the matrix X transpose X.
Okay.
All right. So, if okay, so now if for the matrix K, what we said is that its eigenvectors are
Ma'am, your voice
beta
breaking
1,
again.
beta 2, so on till beta L. Okay, and the eigenvalues we said it is n of lambda L, n of lambda 1, so on till n of lambda L. Right? So these are the eigenvalues and eigenvectors. So again, I can write this eigen equation, right? I can write k of beta k to be equal to n of lambda k times beta k. This is okay. We can write this. All right. So this holds. The first property holds. Now for the second property to hold, which is which you want to see is whether beta k transpose k of beta k also equal to 1 or not. And if not, what condition should be put? So let's try to solve for this. So let's put beta k transpose k beta k. So what is this going to be? So beta k transpose, I know what is my k of beta k from this equation. We know k of beta k is going to be n of lambda k times beta k. But at the end, n of lambda k is just a scalar. So I can write n of lambda k outside, and this is beta k transpose beta k. But again, beta k length has to be equal to 1. That is what we have assumed. So this is nothing but n of lambda k. So what we got is that beta k transpose k beta k is not equal to 1, but it is equal to n lambda k. Okay. So now if you substitute your alpha k to be equal to beta k by n lambda k, then it should work, is what we are saying, right? So alpha k had to satisfy, alpha k had to satisfy, this had to satisfy, this has to be equal to 1. But now this alpha k and beta k are not similar. I mean, they are not same. So what can we set our alpha k to be such that we are able to find alpha k, right? And once we have alpha k, I know my wk can be written as x times alpha k. And now this alpha k won't have any wk in it. Okay. So it's not 1 as I could see, it is n lambda k. So we need to scale it down. So we are setting alpha k to beta k divided by n root of n lambda k. Once we set our alpha k to be this, my formula, I mean, it will satisfy this. If I put alpha k in both these equations, which is k of alpha k to be n lambda k alpha k, and the second is alpha k transpose k alpha k, then it will turn out to be 1 using alpha k to be this.
Ma'am,
Yeah, tell me. Yes, tell me. Are you able to hear me? Um, Sorry, I can't
Ma'am,
hear
can you
you
hear
if
me?
you're asking.
Ma'am, your voice is breaking and you
I
are
can.
fast.
Can you? Um. Please mute yourself.
Can you hear me, ma'am?
I can hear you now. Yes.
Ma'am, my doubt was how can we constrain the length of eigenvector to be equal to 1?
Length of eigenvector to be equal to 1.
Yes.
So okay. So how do you do it? Let's say you had the covariance matrix C and you wanted to, or let's say any matrix to in general. Let's say you had a matrix A and you found its eigenvector. Let's say W is the eigenvector you found. But if you have to make this length to be equal to 1, if the length of W you have to make it to 1, what will you do? If let's say my W is W1, W2, then how do you make the length to be 1? You divide by its norm. So I'll do W1 plus W2 1 root square. Now this will be of length 1.
But ma'am, we didn't did that in the case of beta k.
Yeah, and okay. See, we did not do that. So what was the idea here? We started with our, we wanted to find the principal components for our matrix C, right? I mean, for my data set, which is currently in very high dimension, and and finding those eigenvalues were difficult. It means finding the eigen directions are difficult, right? So, in order to do that, we have set up these conditions, right? We got this condition which is k alpha k to be n lambda k alpha k, and alpha k transpose k alpha k has to be equal to 1. Okay, and what we have what we said is, like, instead of going through uh, finding the eigenvalue eigenvector for C, we will do it for K, and my K is X transpose X. So if this K is X transpose X, we call, let's say, what we said is, let's take its eigenvector to be beta 1, beta 2, so on till beta L, and the eigenvalues will remain the same. Okay, so now if I have to find the eigenvalue eigenvector for um, this matrix K, and for these principal components that we have assumed at the very starting, we have assumed that the length of these the length of these eigenvector should be 1. We have made this assumption, and we have made this assumption with the very starting, from week 1 itself, right? So even here, the length of that beta is, we are saying it has to be equal to 1. Just an assumption it is. And it is coming from the very starting, the assumption that we had made.
Okay, thank you. Ma'am, one more doubt. How you concluded that the eigenvalues of X transpose X and XX transpose are same?
Okay, this is coming from, you can prove it. We have not done the proof, but you can prove it if you want. It's a slightly longer proof, as I would have done it. So this is a fact. I mean, I am not sure if you have studied in MLF or maths, but the eigenvalues for your X transpose X and XX transpose are the same.
Ma'am, that is there in the SVD decomposition, in the like
SVD, it
Gilbert's
is there,
triangle
no?
lecture. It is there. Yeah, in the Gilbert's triangle lecture. Yes.
Yeah. So if you have gone through MLF, you would have seen this, I assume. So for now, you know that they are same, okay? And because they were same, I was able to take this eigenvalue to be this. Eigenvalues of K to be this.
Like non-zero eigenvalues will be the same.
Non-zero eigenvalues. Non-zero eigenvalues. Okay. So with all these assumptions, what we have reached to is that the eigenvectors that we have for my matrix K, which is X transpose X, are going to be useful. And like the okay, let me write it. Right, let me write it here. So K, which was the matrix X transpose X, and its eigenvalues that we found is n of lambda 1, n of lambda 2, so on till n of lambda L, and its eigenvectors were beta 1, beta 2, so on till beta L. So what we do is, see, if we like, if we went through this covariance matrix, which was 1 by n x transpose, x transpose, and finding its eigenvector was our interest. We were interested in finding the kth largest eigenvector. And we saw that this can be given by x of alpha k, right? But alpha k had this term of wk in it. So we wanted to get rid of that. And how did we get rid of that? We found that this alpha k can be written as your beta k by under root of n lambda k, where n lambda, where beta k is the, where beta k are the eigenvectors for the matrix K, and n lambda k are the eigenvalues for K. So now once we know these, once you have this data set X with you, what you can do is, instead of finding X transpose, you do X transpose X. Okay. And since this will lie in n cross n dimension, and we have assumed that my data set, my D is quite large, then doing the eigen decomposition for this X transpose X is not going to be very like difficult. Okay. So it is not going to take too much time. So we do X transpose X, and we find the eigenvalues and eigenvectors for this X transpose X. Okay. And once whatever eigenvectors you got, whatever eigenvalues you got, that can be used to find the principal component for my data set, which is given by wk to be equal to x time beta k by under root of n of lambda k. So now if we have to like write the PCA algorithm for this time complexity issue, what can we say? So the very first thing is, we have this data set D, which is x1, x2, so on till xn, and each of these xi is in Rd, right? And my D is quite large as compared to n. Then what we will do is we find this matrix K, which is X transpose X, and this K will belong to n cross n, right? This will be n cross n. You find the eigen decomposition. Find eigen decomposition for K, right? You found the eigen decomposition for K. So once you have this, what we get is, we get our beta K and we get our n lambda Ks. Then we will set my alpha K to be beta K by under root of n lambda K for every K we have. Okay. And at the end, since we want the principal components, the K principal component, that is going to be X of alpha K. And this is going to be X of beta K by under root of n of lambda K for every K. Is the process clear?
Yes, ma'am.
Okay. All right. So this is how we can deal with my time complexity problem. All right. So now we denoted this matrix K to be X transpose X. So what was the use for that? We'll come to that part. So as we saw that like in case there was I mean if there is non-linear relationship between the features, then we have this something called that I mean we can do some mapping and we can bring this data set to some higher dimension and we will do the PCA, will perform the PCA on that, right? That is what we had started with. So let's say we have this data set xi, as we saw that this we have this data set xi, which was originally in R2, and using this mapping, we mapping this file, we brought this to R6, right? This is what we saw. So what happens in situations like this? Like there was nonlinear features, I mean nonlinear relationship between the features, and doing the PCA was difficult. So what we said is, let's map this data set some higher dimension, which we are doing it using this mapping file. And once we move this data set to higher dimension, we will do the PCA on the higher dimension is the idea. All right. So let's say there is just some mapping file which is moving from RD to RD. Okay, where my D is capital, I mean bigger than the small d. Okay, so there exists some mapping. There always exists some mapping such that you can do k of x comma x dash to be equal to phi of x transpose phi of x. All right. So this always happens. Okay. I mean, not this always happen. I mean, it will happen for certain functions. So, like, now if you have to do the PCA, so as we are saying, we first wherever my original data set is, let's say it's in small d dimension. What we are saying is, using this mapping file, we brought it to this higher dimension, capital D, and we perform the PCA on this higher dimension, right? Just hold on. We perform the PCA on this higher dimension. So like if you think about it, like if we go about I mean if we think about the steps that we have seen in PCA so far, what should happen now? Like now we no longer are dealing with my x1 x2 so on till xn. Now what we are dealing with is the data set phi of x1, phi of x2, so on till phi of xn. Okay, if this is my data set now, then what should we do now? I should find the covariance matrix. I should find the covariance matrix, which is uh which should be what? Which should be phi of x transpose, right? But now, since we are moving from a relatively lower dimension to a higher dimension, then in that case, it is a very high chance that the number of dimensions are going to be quite large, right? So this D could be this capital D that we have, that could be very large as compared to N. So again, what we have seen in that case, like whenever there is this time complexity issue, we can follow this other method. Instead of finding the covariance matrix, which is phi of x phi of x transpose, I will find I will do this phi of x transpose phi of x, right? And I will find the eigenvalue eigenvector. We find the eigen decomposition for eigen decomposition k. We do this, right? And once you find the eigen decomposition for k, then you can find the principal components, which is going to be, so originally my wk was x times alpha k, and we were able to write this as x times beta k by under root of n lambda k. So now in this case, what it should happen? So my wk now should be, instead of x, now you have phi of x. So phi of x times some alpha k is what we will have. Right? This is how we can find the eigenvector. Right? But again, what is the another problem here? Like, see, we move from the dimension, lower dimension to a higher dimension and try to perform the PCA on the higher dimension. But then when we do that, the issue that we saw is that the number of dimension can go very large, that there can be this time complexity issue. So we moved to the kernel side, and I mean we found this matrix K, and this matrix K now is saying that, I mean, you have to find this phi x transpose phi of x, right? And once you find this phi x transpose phi of x, then only you can do the eigen decomposition for K. But again, what is the problem here? The problem here that we face is that what is this phi, right? What is phi? What is the starting
Ma'am,
phi?
your
That
voice
we don't know.
breaking.
So once you don't, um, okay, till where were you able to listen? Is it better now?
Still breaking, ma'am.
Still breaking.
Yes.
Oh, I don't know. Is it better now? Some people are saying yes, some people are saying no. No. Okay. Okay, wait. Is it better? No. Okay, hold on.
Phi is an infinite space which maps higher dimension to lower dimension.
Are you talking about what we are discussing?
Finding phi,
Okay,
inside
okay,
which you
okay.
have put X matrix.
Okay. You're talking about in the same context. Okay, all right. Um, okay, what I was saying is, so what is the problem of the phi here? I mean, we don't know what phi is, right? I mean, okay, once we know the phi, we can do phi x transpose phi of x, but we don't know what it is. So there is this, like at the very starting, what we saw, like this function, there is one special function that we saw, and that function was this x1 transpose x2 plus 1 whole square, right? So when we evaluated that, when we when my xi was in R2 and my phi of xi turns out to be R6, so once we calculated this function, we got this in the form of phi of x1 transpose phi of x2, right? So there are some special kind of functions which we call it as kernel functions, and that can be used to get your phi x transpose phi of x. So one special function was we had mentioned in the very starting, is that this k of x comma x dash can be x transpose x dash plus 1 to the power p. And what we had seen was square, but in general, for if you have any p, or even in that case, if you have any constant here, that works. Okay, so this works. So this is one special kind of function. Like for this, I mean, for this function, when you solve for it, you should be able to find a function, find the mapping phi that will hold this. That will hold. I mean, there will exist some phi such that your kernel function, you can write it as phi x transpose phi of x. So one of this function is this. Okay, so we'll use this function to get phi of x transpose phi of x, and once we have that, we can do the eigen decomposition and we can find our principal components. The other very important a kernel function is something which we call as the radial basis function. So this is when you are like transforming your or moving your data set from any dimension to the infinite dimension. Okay. So if you want to move from d dimension to infinite dimension, then there is this another kernel mapping, kernel function, which is defined as k of x comma x dash to be e to the power minus of norm x minus x dash square by 2 sigma square. So this is also a valid kernel function. There are more such kernel function, but we are sticking to these two for this course. Okay. So whenever you want to move to an infinite dimension, we'll use this kernel basis function or radial basis function. All right. So both of these are a valid kernel functions. So we can use these kernel functions and we can get our phi x transpose phi of x. Now see, this K should be a matrix, right? So what are the components? I mean, for this K matrix, which is going to be in n cross n dimension, right? My K is what? K is phi of x transpose phi of x, right? And K should be in n cross n dimension. So this should be my n cross n matrix. So how do you write each component of these matrix? So each of these component, you can write it as K of x1 comma x1, K of x1 comma x2, so on till K of x1 comma xn. And we will go on till here K of xn comma x1, so on till K of xn comma xn. And
Ma'am,
how
can I
can you
ask a
find these?
query?
Sorry,
Can I
what were
ask
you
a
saying?
query? Ma'am, can we use an x product x dot x into
Can we use x dot?
x into x transpose here, and then we can just likewise center the matrix of the kernel?
Okay, so you are asking about the centering of this phi, right?
No, no, I am saying that you, instead of using these kernel functions, can we use x into x transpose?
No, right? You can't do it. See, why came to kernel part? I mean, why we came to this phi of x transpose phi of x? Because there were no in the lower dimension, like where my data set originally was, there was non-linear relationship between the features, right? So that's why we have to move to the higher dimension to learn those like linear relationship that it has, where we can uh, where we can project our data set and learn the important directions, right? So that was the idea to moving to the higher dimension, and we use this mapping file to move to the higher dimension. So now what this mapping file is doing is that it's taking any data point which you have in the any lower dimension, it's taken to the higher dimension, and then we are learning the PCA, we are doing the PCA in the higher dimension, and from there we are finding the important directions. Okay, so that's why we have this phi of x transpose phi of x that came in. All right. So once we have these functions, these important functions, these kernel functions, we can find and we could see that these kernel functions can be written as there exist such functions for which you can write your k of x dash to be phi of x transpose phi of x. So how to find this how to find this phi of x transpose phi of x goes away, right? Now we know how to do it using these important functions that we have seen. And this is how we can find our kernel matrix. So once we have these kernel matrix, now what we can do? We can follow the same process, right? So if you have to do the kernel PCA, So for the kernel PCA, what do we need? So again, let's start. So where was my data set? My data set was x1, x2, so on till xn, where each of these xi was in RD. And we have defined a kernel, some kernel mapping we defined. And what we're saying is for this kernel function, which is taking your RD cross RD to R, just in case if you're talking about this case different, okay? Don't get confused with X transpose X. This is the kernel function, okay? So this is some kernel function we have defined. Now, what do we compute? We compute Kij, right? And this Kij is basically K of xi comma xj. And this K, this kernel matrix, is given by K of x1 comma x1, K of x1 comma x2, so on till K of x1 comma xn. Then K of x2 comma x1, K of, and so on, K of x2 comma xn. And it will go on till K of xn comma x1, K of xn comma x2, so on till K of xn comma xn. And we find its eigenvalue, we find its eigenvector, and we have seen that this can be written as phi of x transpose phi of x. And we can find the eigen decomposition, of K. Right. So we'll have the eigenvalues and eigenvectors of K. So let's say the eigenvectors are my beta 1, beta 2, so on to beta L. And the eigenvalues are my n lambda 1, n lambda 2, and so on, right? So if these are the eigenvalues, eigenvector, then what do we do? We do alpha k to be beta k by under root of n lambda k, right? And once we have that, we can find our principal components, which is phi of x times alpha k. These are the steps that we follow, right? Till here, is it? Are you able to understand? Are these steps fine with you? Why are
Yeah,
we doing
ma'am.
this?
One more thing,
Okay.
ma'am, I wanted to ask. Here in actually in one MCQ, I found that KXI in the kernel function they have taken two arguments, k x1 and then comma x2 in the brackets equals to x1 transpose into x2. Is this a right kernel function and a valid kernel?
Yeah, yeah. Yes, it is. It is. So, okay, what you can do is you check whether there exists any phi such that you can write k of xj to be equal to phi of xi transpose phi of xj. If you can say it's a valid kernel. Just try it out with a small example.
But without phi, it is written that it is a valid kernel in one of the MCQs.
No. I mean, if it's given the question, I mean, it's not given wrong. It's a valid kernel. I'm saying if you want to check whether it is a valid kernel, this is the process. You
Okay,
check
ma'am.
whether can you find phi such that this happens. All right. If you are able to do, since it's a valid kernel, you should be able to find a phi. Why don't you just try it? You can try to find a phi over there.
Thank you, ma'am.
Okay. All right. So this is how we will do the kernel PCA. But now, see, the problem that we were facing was in like we wanted to do this, right? We wanted to, in PCA, we wanted to do X transpose X. And in kernel PCA, we wanted to do phi of X transpose phi of X. So the problem we were stuck in is like how do you find this phi, right? How do you find this phi? So we what we got is using some special kind of functions, which are kernel functions, we are able to get phi of x transpose phi of x. So this problem was sorted out. So we didn't need specifically what is my phi. But at the end, when we have to find the eigenvectors or the principal components, I again need this phi, right? So what do we do now is the question. So if that's the case, uh, see, in like when you are like looking at the very starting, like very first lecture of week 1, what did we do? Like we had the data set and whatever principal components we got, let's say this is my first principal component, we're projecting those data points onto this principal components, right? And we're taking the projections. So the same thing we will do here. Okay. So what we're saying is, okay, we can't get the uh, exact eigenvector for these in the higher dimension. But what we can do is we can, if if we are saying that my wk is the k largest eigenvalue, or if this is my if this is one of my principal components, then if I project my data set onto wk, what will happen? So like earlier, what we were doing is, let's say this is my x1 and this is my w, right? So this projection was given by the dot product of xi, or let's call it xi. So xi transpose w, and we had assumed from the very starting that norm is 1, so we'll just ignore it. So this is a projection. So now in this case, since xi is now phi of xi, right? So what is going to be the projection, assuming that wk is the principal component for my data set? So it is going to be phi of xi transpose wk, right? So this is going to be my projection. So phi of xi transpose wk, right? So what is the wk now? So phi of xi transpose, and wk is given by, so wk is given by phi of x alpha k. So I can write it in the summation form, and since this is phi of xi, right? So I can write this as phi of some xj times alpha kj, where j is varying from 1 to n, right? Remember that we are interested in the projections. So projections of phi of xi onto wk. Okay. So now this is the projection, and now we can pull this inside, and what we will have, we'll have phi of xi. So alpha k j phi of xi transpose phi of xj. Now this, remember, this phi of xi transpose phi of xj is something that we were able to find, and this was nothing but k of xi comma xj, right? So the projection of my data point onto the principal component wk is turning out to be this sum over alpha kj times k of xi comma xj, right? So instead of doing this, I mean, instead of finding like wk, um, sorry, not this. Yeah, instead of doing this, what we will do is we will find this. We'll find alpha kj k of xi comma xj. Right. So my xi was, which was in originally in RD, small d. Now we are moving this to, I mean, we are now interested in just getting the projections, and we are saying just the projections can give us much more. I mean, we it is sufficient for our problem is what we are saying. So we can't get the exact eigenvectors, but if you are able to do this much, I mean, if you are able to, for any data set, if you are able to get this, which is sum over uh, alpha kj k of xi xj, then that is good enough. And this, we are saying this, do it for all k, right? So we'll move this to this set of projections. So in short, we can write this as alpha kj kij, where j is varying from 1 to n. Okay. So we are moving basically my xi to this set of projections, and these set of projections will be how many? There will be n. So it will be sum over alpha. If you take k to be 1, so it will be k of 1j, k of uh, ij, right? 1 to n. It will keep on going, and k of kj, k of ij, j is varying from 1 to n. So these are some k projections. Okay. So this is what we are doing in PCA. Yeah, someone has a question. Yeah, go ahead.
Yes, ma'am, but we can't find alpha j here, then how can we find that projection?
Hold on. Yeah, tell me. If we, you're saying about alpha k, right?
Yes,
You're
ma'am.
talking about alpha kj, right?
Yes, ma'am.
Okay. So, yeah, again, that is a problem. So what was, let's go back. So what was alpha k? So alpha k was given by x1 transpose, x1 transpose wk by under root of n lambda k, right? And it was going on to xn transpose wk by under root of n lambda k. This is my alpha k, right? And for this, we needed the eigenvectors and eigenvalues for my xx transpose, which in this case should be phi of x transpose. Right?
Can I say
So,
something? Ma'am,
yeah, tell me.
studying this as a transformation matrix.
Which is a transformation matrix? Phi, is it? What are you saying?
Actually, the matrix that we obtain after KPCA is called transformation matrix. It's looking like that.
No. What is the question? We were discussing this, no?
Basically, like when we have eigenvalues, then we take out eigenvalues divided by, eigenvectors we have first, and eigenvalues divided by root and root and lambda k. Lambda k is the basically wait
Lambda k is
eigenvalue
and lambda k is the
eigenvalue
eigenvector. Eigenvalue,
eigenvector
yeah.
eigenvalue, and it is the eigenvector is divided by that in the root form by multiplying it
Right.
with n. It is
Correct.
again multiplied with the centered kernel matrix. Is it that only?
We have not yet come to the centered kernel matrix. I will tell you the process. We have not yet discussed.
A little bit the formula is getting similar.
Yeah, formula is all similar, right? Because at the end we are doing the PCA. So the process are the same. The process are the same, right? I mean, at the end we are doing the PCA.
Yeah, ma'am.
Okay.
Thank you, ma'am.
Okay.
Try to illustrate it with the help of some numerical examples. We would be able to understand in a better way.
The numerical, we will come to it. Not today. We'll do it on Friday. The numerical questions, or there will be one happening day after. All right. Yeah, so far, what we discussed, the steps, is it okay? Is it clear? Okay. All right. So one more issue is that, see, when we were finding this covariance matrix, which was your 1 upon n xx transpose, this was the covariance matrix, and we were interested in the centered covariance matrix, right? So instead of finding the XX transpose, I mean, when you are moving your data set to higher dimension, like when you're moving to, let's capital D, then in that case, what might happen is that it may not be centered when you're moving to higher dimension. So in that case, you will have to center your data set. Okay. So we have this phi of x transpose phi of x is what we are finding, right? So we need to, how do we center this? We get this, I mean, we use this kernel function to get this phi x transpose phi of x. We get this n cross n matrix, but we need to now center this, right? So the thing is, how do you center K? How do you center K? So one way is that once you have this kernel matrix that you have, again you perform the find the this thing. Um, the mean, and you center it. Then this another way to do it is that each of these, let's say if my k is k11, k12, so on till k1n, k21, k22, so on till k2n, and kn1, kn2, so on till knn. If this is my kernel matrix, then to center this, to find kij of C, right? Any element of any Kij I take, how do you, I mean, what should be the entry in that place? So it is given by Kij minus, I mean, you take that element of in the matrix, then you do theta I, indicator of J, you do the transpose, minus indicator of, you take the ith row, and this is a little complicated formula. I think once we do some question on this, I think it will be more clear how to do the centering. Plus P times indicator function of I with J transpose. Okay. But what are these phi, indicator, P, and so on? So here my theta I, so again, this is ith row, I is for row, and J is for column. Okay. I is for row and J is for column. So phi of A, we are saying phi of I is nothing but 1 upon n. Since there are n elements, so 1 upon n you take, and k of I with k. We are interested in phi of I. And how should k vary? K should vary from 1 to n. All right. What is similarly, you do phi theta of j. What is going to be the theta of j? Theta of j would be 1 upon n sum over kj k, sorry, kj, where j is varying from 1 to n. K is varying from 1 to n. What is this p? P is this 1 upon n square sum over kij for all ij. You just basically take the whole element, sum it over, and divide it by n square. Is this this is my p? Then this indicator of or let's not call it indicator. So this is actually a vector. So um, this vector. So this is more like indicator only. So what we will do is like wherever like if I am talking about, let's say j, one of j, right? So at the jth element, it is going to take 1, rest all the places it is going to take 0. Okay, so this is at the jth element. So this is what it means. So like let's say if I want this, right? So this is going to be 0 0, so on, it will be 0. At the ith element you will have the 1, and again remaining all 0. It's what you're going to get. I know this formula is very complicated, but once you do take a small problem, let's say some k, you take a small one, and then you try to center this. We'll do this in the Friday class. It becomes, I mean, you will see what we are doing. These all notations are really complicated to understand. So this is how we can center the data set. I mean, center this phi of, center the kernel matrix, because that is important for moving forward, right? You should have a kernel matrix which you should center, and once you have centered it, you can move on finding the projections. So this is how we can do our kernel PCA. Um, any doubt you have?
No, ma'am.
Were you able to understand? Okay, that's good. So did anyone try any problem? I know someone would have, but what about others? Did you try the problems? Okay, anyone has any doubt?
Excuse me, ma'am.
Yes, tell me.
Ma'am, actually, I wanted to ask about the value of n.
Value of n?
Yeah. So the n
Uh,
refers to which value?
n is a number of data point.
So
So how
it
many
may be
data points you
1,000,
have?
but
It may,
in I think in assignment in some of the problem the value is 1 or I guess 4 kind of.
no. N is basically the number of data set, the number of data point that you have in your data set. So let's say I have my data set to be x1, x2, x3, x4. Then I will say my n to be 4. But each of these xi can be in, let's say, 10 dimensions. So let's say xi's belong to R10. But number
Hmm.
of data points that I have is 4. So I can say my n is 4.
Okay. So in that case, if we have 10, 100 number of data is equal to 100 or 1,000, so our value of n will be this, right? That 100 or
Yeah, if number
1,000,
of
right?
data point in your data set is 100, then I will say my n is 100.
Okay, that's
N
clear.
denotes your number of data points in the data set.
Yeah. And one more thing, ma'am. The in lecture, sir mentioned that the this dimension of this transformed data. Okay.
Hmm.
So there is a formula. I refer discourse for that formula also. But
Hmm.
that is not clear to me. That
Tell me
C
dimension of.
should transform data set.
No. Like what is the doubt in that? You're
Uh,
talking about uh, taking x to taking x which is in, let's say, R2. I am taking it to R6, right?
Yeah, no, no, no,
So
no. The thing is, if we have dimension of the data set is D, and we are
Moving it to, let's say,
identifying the
capital D.
relationship, cubic relationship or linear relationship. Okay, so that formula.
Okay, okay,
What
that
will be the
formula you're
resultant
talking
data
about.
set? Yeah, the dimension of
Okay, okay,
resultant. Yeah, that formula.
okay, okay, that part you're talking about.
Yeah.
So, okay. So, what was said is, suppose your data set has 4 features, okay? So you have F1, you have F2, you have F3, you have F4, right? You have 4 features. Now, what we are saying is, let's say we are interested in finding the cubic relationship, okay? So what we want to do is, my initial data, which is in F1, F2, F3, F4, which is 4 dimension. Using this mapping file, I want to move it to some higher dimension. But what is that dimension? And what we're also saying is we want to capture the cubic relationship. Okay. So I will have my one, right? One is fixed. Then I want all of these, some relationship between F1, F2, F3, F4. So I should have my F1, I should have my F2, I should have my F3, I should have my F4, right? This is one component. Then what would I want? I would want each of these F5s to be related. So I would want F1, F2. I would want F1, F3. I would want F1, F4, right? Then I would want F2, F2, F3. I would want F2, F2, F4, and I would want F3, F4, right? How many are these? 6. That's fine. So I will write F1, F2. I will write F1, F3. I will write F1, F4. I will write F2, F3. I will write F2, F4, and I will write F2, F4. So this is another 6 component. Okay. So once we have these, now I have taken a pair of 2, 2. Now what do I want? I want a pair of 3, 3. I mean, I want a group of 3, 3. So what can it be? So it can be F1,
F2, F3.
F1, sorry, F1, F2, F3. One more thing, I'll come to that. There is something missing. So F1, F2, F3. Then you can have F1, F2, F4, F1, F2, F4, right? Then you can have F1, F2, F3, F4, right? Anything else? That's all, I guess. Or is there anything else? F1, F2, F3 is done. F1, F2, F4 is done. F3, F2, F3, F4 is done. I think something else is missing, no? What else?
Can we add F1 square, F2? That's also cubic relationship, right?
No, I will come. I'll come. That's why I said I'll come to that. Um, but this is 4, and I want to choose 3. So 4 choose 3 is
Ma'am,
4, right? Or what is the other one more? Huh?
Have it
1, 3, 4. 1, 3,
134.
4 is done. Oh no, not done.
124
Okay.
and
F1,
134.
F3, F4. Okay. Okay. So this is another 4 we have written. Then at the end you have F1, F2, F3, F4. This is one possibility. But there are more to it. I mean, in the lecture we have seen only this, but there are more to it. I mean, I'll see. Like when very starting, this part. What we had done is F1, F2. We were interested in the quadratic relationship, so we mapped it to. I mean, there is one, there is F1, there is F2, then there is F1, F2, and then there is F1 square, there is F2 square, right? So same thing should hold here as well, right? So I should have my 1, I should have my F1, I should have my F2, I should have my F3, I should have my F4. This is also good. But now for the quadratic relationship, it's not that we have these 6 component, there should be more. So there should be my F1 square, there should be F2 square, right? F1 square, F2 square, F3 square, F4 square, F5 square, F6 square, right? They should also be there along with these, which captures the quadratic relationship. So we should have 6 plus 6 of those. This is 4, this is 1. All right. Now for the same for the cubic part, it's not that we should have just these 4. We can have many more here as well. So if I'm taking F1, F2, F3, I mean, along with these 4, I can have maybe F1 square, F2, F3. Oh, sorry, F1 square, F2, F2 square, F3, F3 square, F4, and so on. There can be many such possibilities. You can count down additional terms that will get added. And then, of course, for the 4 component, we have just one. So there are more to it, not just, it's not that you have to do 4C0 plus 4C1 plus 4C2 plus 4C3. It's not, it doesn't get over here. You have more, you have more number of dimensions that will get added. Is it okay?
Yes, ma'am. So in lecture, sir only did that C choose
Yeah,
D0,
some
right?
part,
Yeah.
some things were missing over there. Yeah.
Because when I referred the solution in discourse, in that solution they consider the formula. Okay, so that using that formula, I again revisit the lecture and created the using formula. I calculated, so it went the huge number. So that's why I got confused.
Okay.
So
Can you share the discourse post with me? Maybe in the chat you put it here. Okay. It's done here.
yeah, ma'am. Actually, yeah, just a minute. I will share it with you.
Yeah, you can share it in the chat.
Ma'am, please try to provide the recording of the session.
Yeah, sure. I will provide. Yeah.
Ma'am, will you provide it in the discourse or in the calendar only we would be able to access it?
In the calendar, you should be able to view, and the live streaming is visible. That will also be on the calendar. Notes by any chance, we can upload it on the portal. I mean, yeah, but it's very rough. I don't know how you can use it. But okay, if it's useful, we'll get it uploaded.
And one more doubt I had.
Yeah, tell me.
Ma'am, what is a linear kernel function?
Linear kernel function. So we saw two kind of functions, no? What are the two functions that we saw?
One was x transpose into x plus 1 power up to the power whatever we want. If we want a polynomial, then we will select the degree equals to 2.
Yeah, right.
And
But I
another
don't know.
was exponent.
Where did you see linear in there? Did
This
you read
kind
it
of,
somewhere?
yeah. Actually, it is present in the Python doc they had provided.
Okay. Okay. I will check. I'll check.
Thank you, ma'am.
Yeah. Thank you. Anyone else has any doubt? I see a hand raised. I don't know who is it.
Ma'am, where available these notes?
These notes will put it on this portal.
Okay.
Excuse me, ma'am. I got the post, but I don't know how to share it.
You just put the link in the chat.
I am on the mobile. Okay.
Okay.
I don't
Okay.
know.
Maybe
I
I'll
don't
take a
know.
look. I will take a look.
Let me paste over here the. I got the link. I don't know whether it is link for the post or yeah, maybe yeah, true. Just access it, yeah. So yes, in
Yeah,
some
got it.
post the formula is like
Yeah, I got
d
it. I
plus
will take
r
a look there.
minus 1. In some cases there is minus 1, and in some cases there is not only d plus r. So I'm not sure how to take the relationship value because the number of dimension is we got from the question itself, but how to uh, take the value for the relationship, so that's the part I'm really confused in.
Okay.
Are we
We'll
able to
take
access the post?
yeah, I am able to access it.
Yeah. So I just got one person shared the whole theory notes on that formulation. So I
Okay.
didn't get, I'm not able to find that images because that person pasted the images over there in that post.
Okay, okay. All right.
Okay.
I'll take a look. Okay. And
Okay.
if there is something, I'll reply in the same discourse
Okay then.
post.
Okay ma'am. Thank you ma'am.
Okay. Thank you. Right. We'll stop the recording.
Ma'am,
Yes, Kiran, right? Yeah, Kiran.
yeah, is there a OPP for this course?
Is there?
OPP.
Yes, there is OPP. So one OPP is happening on 5th October. So if you have not done the workshop in the last term, maybe next term you can do it.
Sorry, can you repeat that?
The OPP will happen in the next semester. I mean, after you complete the course.
After completing this course.
Yes, after you complete MLT, then you can write OPP.
Then will it be
So
part of
OPP is not
MLP?
okay. OPP is not a part of the course, but if you do this MLT OPP, you get some activity points basically. So that is how it
Like
is.
bonus marks?
No bonus mark for OPP. Bonus mark is there for doing the programming assignment, but not for OPP. If you attend OPP, you get something called activity points.
Okay.
Okay.
Okay. And for like MLP, the OPP is
MLP it is
separate.
mandatory. Yeah, MLP it is
Okay.
mandatory.
Okay.
Yep.
Where can I check those details, like OPP details?
I think it should be there on your grading document.
Like the
And there is a
timeline.
special section on portal where you can check your activity points doc.
Section.
Just the grading document and activity point doc should be enough.
Is it placement activity points?
Yes, yes.
Okay. Okay, thank you.
Okay. All right. Thank you, everyone. So next time we meet, we'll do the problems on week 2. Okay. All right. Thank you. Bye. Have a good day.
Thank you.